Alright, let's get started with the last easy LeetCode problem of the grind 75 169 problem list. Today, we're going to be going through, let's see, number 977, squares of a sorted array. Given an integer array num sorted in non-decreasing order, return an array of the squares of each number sorted in non-decreasing order. Okay. Let's see. So, like the LeetCode thing at the bottom says, the easiest solution would be to square each element, then sort again, which would be O of n plus O of n log n, because now we know that Kotlin's sort is based off of Java's sort, and Java's sort is based off of quicksort, even in the case of an integer array, rather than anything like a radix sort. So it ain't linear. So that's just O of n log n. We just drop the lower part. So O of n log n solution would just be to square each element, sort them. Pretty trivial stuff there. Could you find an O of n solution, so a linear time solution, using a different approach? That's a good question. Okay. So what's the main problem here? For positive numbers, there is no issue with just squaring them. And, well, no. I thought that was the case, but no, that's actually not. The problem happens because we have negative numbers, which in this case are not great, because we might need to swap positions. I have an idea. I'm thinking of maybe doing something like a two-pointer approach. Apologies. So, a two-pointer approach to this problem. And I have no idea if this works or not, but this is the first thing that I was thinking of. And this is partially because I've been thinking about, in terms of just a retrospective on all the easy problems that I've gone through recently, and sort of just trying to break down all the problems into sort of the core patterns that you learn when going through the grind 75 list, and sort of the core patterns that you pick up from there. One of them is the two-pointer approach, and it turns out that the two-pointer approach actually has applications not only in linked lists, where they are pretty popular. See the example of reversing a linked list, or finding the middle of the linked list, or finding a linked list cycle, right? Two of those are fast and slow pointers. The other one is just a runner, basically, a runner that goes a little bit faster than the other, one faster than the other. But a two-pointer approach also has applications within arrays, in the context that you might want to consider having one pointer at each of the ends, and then manipulating the array in some fashion. So, let's break this down, this problem, or what I imagine a approach to be. So start each pointer at each end, so 0 and size -1. check to see if the square of the left side will be larger than the square of the right side. If yes, then swap. If not, leave them as is and square. Well, we want to square in both cases, but to the effect that if the left side has a larger value, then we swap. So 10 and 4, so 16 versus 100, we don't swap there. Then, if we swapped, we want to, let's see, if we swapped the values, then we want to move the right side down and leave the left side up. If we did not swap, we only want to move the left side. Or, sorry, no, we want to move both sides. Both sides to make the next comparison. And this is due to a fact that we have within this array, that because the array is sorted, we won't have a situation, as far as I know, where we would quote-unquote miss a swap. And this is because as we go closer to 0, the magnitude gets smaller. Is that something that we need to account for, actually? Let me think. That's a good question. I'm going to actually put a pin on this. Just put a dash there to confirm. But if we swapped, then we want to move the right side down and leave the left side. Because we basically want to find where this left side of the array fits, right? So we compare -4 and 10. Obviously, 100 is larger than 16. We don't swap them, so we just move the right side down. Now we compare 9 versus 16. Of course, 16 is greater than 9, so we move the 3 and we swap the 3 and the 4. And at that point, the 4 here is now in place. The swapped value will be in place. We don't need to care about it anymore, because as we move up away from the negatives, we decrease in magnitude, and when we go above 0, the numbers squared will always be less on the left, because that's just from there it's just pure magnitude, right? We don't need to worry about that, because at the far end we have basically the maximum. So continuing our example, so 10 and 4, we did not swap, so we only moved the right side, and the 10 is where it should be. 4 and 3, the 4 is greater than 3 in magnitude, we swap 3 and 4, and then we move the right side down. Interesting. Okay, so maybe we don't actually want to move both sides then. Because the 3, if we did not swap, let's see. So we swapped the 3 and 4. So now, let's just make this a little bit more clear. We swapped, so we moved the this pointer down to 0, and we leave this pointer at 3. Now 3 is greater than 0, so we move that here. And since we did swap, we want to move the right side down. So now the 0 would be here, and the -1 would be here. And here it would be fine. So we did not swap. So we moved the right side down, and we moved the left side up. Because if we did not swap, then from my understanding, it seems like we do not need to worry about it, because then that means that the left side is where it should be with regards to actually no, we didn't swap, or we didn't move the left side up when we did not swap for the first one. Okay, so in this case, if we did swap, we just do that. If we did not swap, still don't move the right side down, or still don't move the left side. Move right side down. We need to find the swap point. And then here it would be terminate when left is greater than right, or greater than or equal to right, or when I guess right breaches. Technically, if it's left or when left is less than or equal to right, we can just say when right is equal to 0. Less than or equal to 0 technically, but it shouldn't breach 0 regardless, because we're keeping the left side sort of we're sort of leaving the left side where it is, basically, and we're sort of keeping the left side sort of as a pivot. So this kind of actually reminds me of sort of like a sort of pseudo, or at least like the pivot step of the quicksort, where you choose a random pivot, or you choose the middle as a pivot, and you move all the numbers that are lower to the left side, and then all the numbers that are greater to the right side, and then you basically divide and conquer for each of them, for each of those subsections, essentially. At least that's how I remember quicksort being. I could be wrong on that. It's been a while since I've done quicksort. Let's see. Yeah, so effectively we are doing like a quicksort type of thing. So, let's see. Let's run the same example on example 2, and let's actually like comment it out so I'm not just talking and losing some of y'all. So -7, -3, 2, 3, 11. Compare -7 and 11. Less, don't swap. And I'll put a star where the comparison pointers are. -7, -3, 2, 3, 11. Now we're comparing -7 and 3. Compare -7 and 3. -7 squared is greater than 3 squared. Swap. So now we have 3, -3 to -7, 11. Actually, this should be 121. Because we would 49. Then we would do compare. So move this down again. Compare 2 and 3. 3 squared is obviously greater than 2 squared. Swap. So now we have 2, negative 3, 9, 49, 121. We would do compare 2 and negative 3. This should be 3 and 2, just to be clear. 2 squared, or less, don't swap. But in the case that we do not swap, or really in all the cases, we should always square the right pointer because it's done at that point. Then we do square the middle, or square the 0, and then return. So in this case, the runtime is O of n, and that is first to copy the array, because we need to return an int array, right? Or actually, no, we can do it in place. We can do it in place, right? It's O of n because where n is the number of elements in the array. And this is so because at most we are comparing the elements from right to left until it hits the end. Sure, we are making 2 comparisons at each point, and perhaps that there is a better way to handle this so that we don't have as many comparisons. Of course, we could also consider doing something like we could try doing something like a binary search to find like the perfect location for the swap. I don't think that's really strictly necessary, at least for now. So this is what I'm gonna go with for now. But basically, we're making at most 2 comparisons for each element in the array. So here, then here, then here, then here. So basically, we're comparing here, last and the first, fourth and the first, third and the first, second and the first, and then we just do one operation on there. So really, it's actually one comparison, but we're just comparing 2 numbers. But in any case, it is a linear algorithm because there is no growth with respect to, or there's no additional growth besides linear. If we add more elements to this array, we would just have to start further down and have more comparisons before we hit 0. So I think this is a pretty straightforward algorithm. I think that this runtime fits in the O of n approach, the linear approach that is stated in the follow-up. And I think at this point I'd be pretty much ready to code it. So let's get started. So we can say val right is equal to nums dot size minus 1, size for collections, length for strings. While right is greater than or greater than 0, we can say if nums at 0, let's see, how do I square numbers in Kotlin again? Can I do that squaring thing? Let me just do a quick playground, or just square. Let's see. I could just do like a multiplied by itself. It's not the most elegant of solution. I could also do like a, yeah, we could do that. We can run a math.how nums at 0 to 2, right, using Java. That's also something that I feel like I sort of just started to discover in terms of just like figuring out Kotlin is, again, a reminder just that Kotlin is built off of Java, the JVM at the very least. So, and it uses a lot of Java like underlying standard library stuff. So don't be afraid to use Java library stuff. Um, in any case, MathPow is one of those Java standard library functions just to the power. So I believe it should be base to the power. So we take our left, or whatever is on our left edge, we compare that to the right side. If that is greater, then we want to swap. And then after that, we want to just nums at right is equal to nums at right, or MathPow 2. Maybe we could do a times equals 2 here. I'm not actually too sure about that, but that's like a small, maybe like a small optimization. Maybe not even an optimization. Reduces function calls at least. So if the square of the left anchor is greater than the square of the right anchor, then we want to swap them. And at that point, we would do temp, val temp, and this should be a var, by the way, because we're changing it. So val temp is equal to nums at right. Then we can say nums at 0. So we'll set the temp to the left edge. We'll swap the left to the right. And then we'll set the right to the temp. So this is just a simple sort of two-way swap with a temp. We just swap the values, and then we square it. And then right is equal to nums MathPow, and then return nums. So we start off by declaring our right edge as num size -1, right? That's just the right edge. Pretty simple, straightforward. While our number is greater than, while our right edge is greater than 0, technically you could have greater than or equal to, but it's just a very, very small optimization that we just jump straight to the end at that point. We just square the number because we're at the same index, right? If the left edge is greater, we make this comparison here with here. Then we will swap the numbers because then at that point then the magnitude will be greater. Then our right side is, whether it's the swapped value or it is the original value, it does not matter. That right side, that right edge is done. We don't need to care about it anymore. We square it and we move on so we square it here and then we move the right edge down. Once we hit right is equal to 0, so we're at the first element. That first element hasn't been squared yet, so we square it again, or we just square it for the first time rather, and then we return our original nums. So this is an in-place solution to this problem, where we are just taking the numbers and swapping them where appropriate, squaring them once we're done with them, and then returning the same structure. Again, this is actually very reminiscent, in my opinion, of something like the pivot step of the quicksort. And maybe we'll even see a problem that just says implement quicksort or something like that once we dive into the mediums starting tomorrow. So I think this is a pretty alright solution. Let me just check the constraints. The minimum number of values that we can have in our array is 1. Which it works. It'll just declare this is not greater than 0, it's equal to 0, so we just square it and then we return it. We've already tested it with 2 examples in which we have both no swap and swapping, and we checked that our algorithm handled both cases. And I think at this point this is it's fine. I would be ready for a submission. And yeah, in terms of places where this could go wrong, using a while loop is always a risk. You need to make sure that you're actually incrementing or decrementing your counter, otherwise you just get stuck. in this case, because we're not moving the pivots around a lot, I think it's actually a pretty risk-free. In some cases, like for example, when I was doing the sorted array to binary search tree, that one was a mess in terms of the indices because they were changing around a lot and like trying to find the midpoint and things like that. Still need to review that, and I actually have a plan for a review in the future. But yeah, in this case, I think the main point where it could go wrong is here, and maybe with the swap, if you don't do it correctly, maybe you accidentally save it to the value. Maybe you accidentally save it to a value that you end up overwriting. Right. Like if I saved it to right there, then that wouldn't be correct in the temp. But yeah, other than that, it seems pretty correct, and I'm gonna toss it in for just the examples, running through the examples again. Right, that's another issue. Okay, so right, so math.pow is strictly for doubles. I kind of forgot about that. Or doubles and floats, right? So this is not a particularly clean solution anymore because of the amount of casting that we're doing. Actually, we don't need to worry about this for now. We just need it. We only need to compare it there. But for here, we need to cast it to int because this will be of type double. This will need to be to double. Ooh, wait. There you go. To double, 0.0, and to int. I'm not actually sure if the int array automatically casts values that you dump into it. That's a good question. Let's actually do some investigation. Does it automatically truncate the values as you place it in? Okay, it does not. So I guess you have to keep it there. I know that we already tested one of them, so let's just launch both of the test cases. And then let's throw in a submit. I think I'm at the point where I'm fine with this submission. We talked about the runtime and stuff. Ooh, okay. Look, interesting. Looks like we got a wrong answer. Okay, let's see where we went wrong. Hmm. So we swap 1 and 5. That's fine. Then we don't swap 1 and 2. And we don't swap 1 and 3. That's a good question. In that case, if we do swap a value on the left, then do we swap? If we do swap a value with, then do we need to move the left side, the left edge? So why isn't this working? So we swapped 1 and 5. That's fine. That's correct. However, the problem is that after we swap 1 and 5, 1 is now the minimum. And since nothing is lower than the minimum, then we don't swap anything. In that case, I'm thinking of if we want to do something like a reversal of what we did with the swap, where if we do not swap, then let's see. If we did not swap, that means that the right side is fine as it is. If we did not swap, is the right side fine as it is? No. Because we did not we swapped 5 and 1. We did not swap 1 and 2. If we did not swap, then perhaps it is an indication that it is the left side that is fine. And how could that be? If we do not swap, then that means that the left side is fine as it is. But is it fine for squaring? This is fine, we swap. Then we swap again. Then we swap again. Then we do not swap. Hold on. Okay. I've come to the realization after like 10 to 15 minutes of doing this that negative numbers suck. Negative numbers really suck, because it seems like in what I've done with just done some quick writing, things like that, but it seems like there needs to be a special carve out for negative numbers, specifically on the right hand side. And what I mean by that is that if there is a negative number on the right hand side and we do not swap, then there is a chance that the number below it is greater in magnitude than the number that we're at. A chance. If we did not touch that number yet, which in this case we will not. And that's really weird. Because I don't know, it's difficult still for me to really wrap my head around it. I'm still trying to come up with like a really good and like meaty explanation for sort of why this is the case. But the most I can say is that, like, yeah, when it comes to negative numbers, if we're in the non-decreasing order, the number below it will be greater in magnitude versus the number above it in the case of a positive sort of non-decreasing order. As such, we probably need to make a carve out for it. Though, I'm really not sure if this will actually work for the other cases. So I'm going to have to backtest this and just quickly make sure that it actually does work. And that I'm not like screwing myself over. So, let's see. So the idea if the right hand side has a negative number and we do not swap, then move left hand side up. This might be a little bit weird, and I'm not sure if we need to also consider the value of the left hand side. So going back to here, negative 7 and 11 don't swap. Negative 7 and 3 swap. 3 and 2 swap. 2 and -3 don't swap in this case. And since the 3 is a negative number, we move the 2 up to here. And now it's on the same tile. The problem is that the original value is still not squared. The original value won't get squared. In fact, I don't think any numbers that are below the left-hand side would get squared, unless we also square numbers between 0 and left-hand side. Because it'll be just skipped. For example, let's toss in the -5, -3, -2, -1. Add a star here, add a star here. Compare -5 and -1. -5 squared greater than 1, -1 squared, swap. So now we have -1, -3, -2, 25, with the comparison at -2 and 1. Compare -1 and -2, don't swap, right hand side less than 0, move left hand side up. So now we have -1. Actually, what we could do, square left hand side. So now that becomes 1. We have -3, -2, 25. Compare -3 and -2. -3 squared greater than -2 squared, swap. -2, 9, 25. And then now, let's see. Left hand side would still be here. Right hand side would still be here. Then square right hand side. Basically, we would go until left hand side is less than or equal to right hand side. And I think this makes sense. But again, I'm just trying to find a counterexample. And as I've been told, if you can't find a counterexample, it's either A, because you haven't thought of a counterexample that works, or B, because there is no counterexample and you are correct. I'm not confident that this is the second one in this case, but there's not much that I can do. I think this seems reasonable, that we move the left-hand side up and then we square it. Because if they're both negative numbers, do they both need to be negative numbers? Let's do a -2. What was the example that I actually had here? I had a good example here. -2, -1. One? Let's try that to see if that makes sense. -3 and 1. -3 squared greater than 1 squared, swap. So now we have 1, -2, -1, this would be 9, star here, star here. 1 and -1, same, don't swap, right hand side less than 0, move left hand side up and square. And then it would be 1, -2, -1, 9 with the comparison on here. -2 and -1. So no, not both of them need to be negative. -2 squared is greater than -1 squared. Swap 1, -1, -4, 9. And now we have both here. And then we would do square right hand side. Cool. Okay, so I think this seems to work. I don't know, maybe we'll hit another snag, another incorrect. But this seems to work. Again, the reasoning in a very casual way is that if we have a negative number on the right hand side and we do not swap, there is a possibility that there is a negative number of greater magnitude below it that we haven't explored yet. Therefore, we need to move the left hand side to make sure that that we haven't missed any of the numbers. So let's retool this. So we'll need to add a 0 for the left hand side. While left is less than right, we can say val original, or we can say var has swapped is false, is true. So basically this is just a flag for us to know whether or not we have actually swapped. If not has swapped and the number on the right hand side is less than 0, left plus plus. But we also want to do nums left is equal to math pow nums left dot to double 2.0 dot to int. So square the left side, move it up. Otherwise, we can do this. By the way, just a quick shortcut. Something that I have in IntelliJ, maybe in other IDEs as well, but I'm not sure the hotkey. Control Shift up and down the arrows lets you move lines of code or selections of code up and down lines. It's really helpful if you need to just quickly surround something in a lambda, and you don't have like sort of. I think LeetCode is a little bit weird in where if you surround something, maybe. Okay, it does have that, but yeah, sometimes it's just useful to have the additional way to just move lines quickly in up and down lines. So we still square the right hand side, we still return it. We added our provision here where if we haven't swapped and the number on the right is less than 0, then because if a number less than 0 on right hand side, there is a chance for a number on its left to be of a greater magnitude because of how sorting with negative numbers works, right? So if we have a number on the left that is negative and greater than magnitude, we do want to consider that. So while left is less than right, we just want to hit until this point basically where they overlap, and that's perfectly fine with us at that point. We check, for each time we have this, we just have has swapped, and then if the numbers are if the number on the left is squared is greater than the number on the right, we swap them. we set this has swapped flag to be true. If it hasn't swapped and the number on the right is negative, we go through that carve out provision that I talked about. Otherwise, we will just go through our regular routine of squaring whatever is on the right because that part is done. And then we move on to the next one. I am curious about this an edge case though, where we maybe could run into some issues with the 0. Let's see if it happens. I'm not gonna do a full like run through with this one. I'm just gonna quickly this -2, -1, 9. Then this would be 0, -2, 1, 9. No, actually this would remain -1 because that's less than. So then, yeah, so that would actually remain the same. And then that would be 0, -1, 4, 9. And then 0, 1, 4, 9. Okay, cool. So it seems like it works. Let's run our test cases. And then we'll also run through this one. Run through our standard test cases. This should be nums on the right. Okay, so our standard test cases still work. Let's plop down our new test case of only negatives. Interesting. Let's see. Why didn't that work? That's a good question. We don't want the right-hand side to move, which we didn't. We swapped. So we did that. It looks like nothing has changed, which is really, really odd. -5, -3, -2, -1. We swap, so that's -1, -3, -2, 25. Now the focus should be on -1 and -2. And in -1 and -2, because it's that one is negative, then we should move the right-hand side, and it should be -1, 3, -2, and 25. However, that doesn't seem to be the case. I forgot to replace all the 0 indices with the actual proper left index. That makes sense. Whoops. So now this should be correct. Okay, cool. I thought I was going crazy with my solution. Let's run back with my original test cases just to make sure I didn't break anything in the meantime. Okay, cool. Let's do like -3, -2, -1, 0. And then we can also do some other fun ones like tosses a 1 in there just to make sure. Okay, cool. We found another situation that broke it. Which is good because we found a solution that broke it, or we found a problem that broke it before we actually submitted. Let's see what went wrong here. Once -3 swaps with 1, that's fine. 1 swaps with 0, that's fine. 0 doesn't swap with -1. That's fine. Zero doesn't swap with -1. That's fine, right? Hold on. Now I need to model this out because it's starting to get a little bit a little bit dank for me. Let's see. 1, negative 2. We would have swapped in that case. Negative 1, 1, 9. Alright, so we swap 1 and 3. Then we swap 0 and 1. So now the star is here. Left hand side is here. Left hand side is there. Right hand side and left hand side. That doesn't change anything. So now we go negative 2 star, negative 1 star, 1, 9. And that should have swapped. Why didn't it swap? Because in that case, that's just the standard case, right? Is there something that I'm missing? Like, is there a typo in my code? Because it seems perfectly reasonable here. We don't swap, we move, we double, and we move up, right? Oh, it's because we didn't. Oh, it's because we did swap it. But we didn't account for the fact that that's there. I see. Okay. Oh, that's more complicated then. Man, this problem is actually shaping up to be pretty difficult. I still think that the two pointers approach is the correct approach. It's just that there's probably some lot more there's probably a longer process before arriving at the solution. Let's see. So what is the problem now? The problem is that we're swapping with it seems like almost we're swapping prematurely. In the sense that, okay, there, then we swap with you, right? So we swap 0 and 1 like that. And really, this negative 2 should be swapping with this 1 right here, I feel. But how do we accomplish that? What if, rather than changing... What if we go back to here, and we say that if we don't swap, then we don't move the right-hand side. We move the left-hand side. But I feel like then I'd have to go back and do some regression testing on that now. Oh boy, this is shaping up to be quite a problematic problem, actually, for me. So what I mean is that rather than doing like rather than some weird like right hand side less than 0 thing, what if on no swap move left hand side up, on swap move right hand side down? Is this... I remember thinking about this beforehand. I wonder if it's just because it didn't survive the initial examples. Let me see. You here. That means that you don't swap. If you don't swap, what does that imply? If you don't swap, that implies that the left-hand side is less than the right-hand side. Let's see. Huh. Seems like in this case... Okay, what do we actually want? We swap 1 and 3 and we move this down. That is fine. Here we swap again. And this is not fine. To move it down again. Why is this line problematic? This line is problematic because by moving this pointer down, we still have room for this -2. So swap, move right hand side down. That's okay. Would it be okay? Sure. Then we swap, move right hand side down again. Not good. Why? I feel like there should be a simple explanation for this. And again, the problem comes in when we're dealing with negative numbers. And this sucks. I'm gonna give it a little bit more of a thought off camera because this is probably gonna take a longer time, and I'll be back. Okay, I have no idea if this will make it into the final cut, but I have a different approach. Now, it basically relies on the fact of whether or not it swaps, and then run some logic on there. I'm gonna first start by submitting it to see if this is correct. Otherwise, this might just end up being like a 5-second clip. If it does work out, then I'll go ahead and start explaining. Looks like there's another issue. Let's see. Man, this problem is truly something. And I'm not even sure if I'm done yet. Like, I feel like I'm close. But it's just, there are just so many cases to consider. I'm putting a lid on this problem for now. I decided to just say screw it and not deal with an in-place method for now, which, looking at the memory usage, has probably screwed me over on that part. There probably is an in-place way of handling this. I don't have enough time right now to figure it out. My new solution is pretty simple. It still goes off of the same idea before, that at each end of the array, and as you get closer to the middle, you have the greatest of either the negatives or the greatest of the positives. You compare the two and choose one to add to the array, and then you just ignore the other one. So you pick one, and then you move it over towards the middle until it gets over a threshold, And then you just set it to 0, in which case it will never be greater. So in that case, well, except for zeros, but yeah, that's also handled here, just the else case. It'll just add the positive one. Nothing too spectacular. It works. Looks like it's relatively average for runtime, which is good. I think I'm going to leave it here for now. And just to give you some perspective on this one, I started this problem at around 11 this morning. It is currently 5:52. This is including like some time for like lunch and like taking a shower and like exercising, but like this one was rough. But I'll have to come back to this one just to see if there's something that I don't know. I'm really curious as to whether or not I was actually close to the solution, close to the most optimal solution with I think it would be a linear runtime and constant space. Because this two-pointer method seems like it's on the right track. I just don't quite know how to handle it with all that weird stuff with the manipulation of in-place shenanigans. In any case, that's the last LeetCode easy problem, even if that one didn't feel so easy. And tomorrow we start on the mediums. My plan for study, as of right now, is to continue to do one problem a day with the medium problems. And off camera, as far as right now is concerned, off camera, I will also be studying from the beginning one of the easy problems. Now, my review of these easy problems may not necessarily be full walkthroughs of these problems. Basically, I'll go over the problem myself, talk about the problem, approaches, and then sort of just map it out. And as long as I feel like I can get a good handle of it, I'm fine with not necessarily coding it out. Though I might end up doing that for some of the more problematic problems, such as the tree problems, and of course the one that we just went over today. If you're interested in doing that, I encourage you to do something similar. If you have a better idea of how I could study, I'd greatly appreciate leaving that in the comments below. Other than that, I hope you enjoyed seeing me suffer. Hope you learned something at least. And I'll see you for the next problem.